As our main topic of today's seminar is energy security and how fuel cells and hydrogen can contribute to energy security. So I just would like to show you some graphs to illustrate where we are currently and actually what or how fuel cells and hydrogen can help us out with this energy security and especially focusing on conversion efficiency. If you look at the world's map, then you see self-sufficiency of different countries, which means that how much each of these countries can actually live by themselves. And the dark blue color is very good self-sufficiency, and the lighter you go, less you have self-sufficiency. So you see that Europe, compared to the other world, is quite pale. So we don't have so much self-sufficiency in energy. And if you look more closely, then in European countries of all energy usage, you can see here darker color means less energy self-sufficiency or more dependence, and the lighter color shows that you are more. But it changes quite drastically when you look at how it looks with natural gas, for example. Natural gas I'm bringing in because if you want, with existing technologies, a little bit cleaner environment, so and then using natural gas you can get it, but the dependency highly goes up, and this is mainly because of this picture. So this is very, very bad. If you look at this quite huge red area, so the whole eastern part of Europe is dependent nearly 100% of Russian natural gas. The more west you go, the less is dependence. But this is huge. And this is something about security, because you never know what will happen, and that's why we have to get ourselves more self-sufficient also from the primary energy side. Or is it possible? Because, yeah, but this is Europe in general. So you can see Estonia, we are in pretty good shape, only about 7%. We depend on energy import. Europe's average is around 53%, Eurozone about 60%. So about half is what we are depending on imported primary energy. Just look how energy is flowing in Europe. So on the left side we have input from a primary energy, and on the right side is a consumer side. So the lower part is a transportation, and as it was mentioned, the efficiency of transportation is extremely low. But if we leave transportation out currently and look what happens actually here in power production or energy we are using in industry and the households. So the total primary energy mix looks like this. We have majority of energy is produced by coal, natural gas, and then nuclear. But if we go back to this energy flow chart and look specifically how electricity is produced, and most of electricity is produced currently in a centralized big power plants and delivered to customers through electricity grid. So, and in centralized energy production, we see a little bit different primary energy mix where actually coal and nuclear are quite equal, and natural gas and renewables a little bit less, but also quite equal in picture. And if we go back to this same EU 28 energy mix, so and looking how much of this centrally produced energy is received by end users or customers. So we can see that about over 60% of primary energy is just lost somewhere in between. So all these centralized systems are highly inefficient as they are now. But if you look different countries, Germany, for example, which is largest energy consumer in Europe, the energy mix is is different than Europe total, but total efficiency is also below 40%. It's about 38%, and the share of renewables quite small. In Estonia, we have very dark picture here. Most of energy is produced by burning a stone, which is very inefficient, as we know, and highly polluting. Part of renewables in Estonia, actually a little bit changed here. This is graph from 2011. Current wind share is about 5 to 7% maybe. It's better now, but still it doesn't change a lot big picture, and we are about 40% of efficiency of the system. This is US, for example, extremely low, and from transportation you can see how much is flowing in and how much is really actually used. So it looks very bad, and this is only due to extremely low efficiency of a system, which means that you have to input a lot of energy, a lot of primary energy, majority imported from unstable parts of the world. So global demand is growing. Whatever we are doing, we can conserve energy, we can take measures as individuals, as a society to conserve energy, but still society is electrifying, and mainly you can see the growth from the non-OECD countries, developing countries, China, India, and this is part of a world where energy consumption is growing heavily. So up close to 50% is predicted global power demand grow between now and 2040. So really, and if we still continue to run these inefficient systems, I think we will soon meet some kind of a very bad crisis. So what actually can we do? So I think something what can save us here, so to say, is to decrease primary energy consumption just by increasing power conversion efficiency. So it's actually the only way to reduce primary energy usage. And Robert earlier also showed some efficiency percentages of different generation technologies. Here it's graphically, so you can see that fuel cells are really most efficient technology to convert primary energy to secondary electricity or heat. And then from fuel cells you can clearly see that solid oxide fuel cells have the highest efficiency at the system level, and not depending on the power range. Really you can run small under 1 kilowatt systems or 100, 200 kilowatt systems, or even bigger at the same high efficiency. Of course, these combined cycle power plants can run close to the same efficiency, but again they are centralized, and then we have grid issues, and because if we have power outage, so usually this is not a problem from the production side, it's always about grid. But if you produce power locally, so gas grid practically never fails, so you have always fuel available for local power production. So this is one illustration again, what is the difference actually, and where are the losses at the system level if you compare internal combustion engine, for example, to the fuel cell system. So you can clearly see how much, or pretty good visual picture, how much primary energy, gasoline or natural gas you have to put in, and how much you get out of useful electricity and heat, and the difference is huge. Here we're talking about distributed generation. So for the fuel cells, as also has been mentioned earlier, we have a lot of different applications actually where we can use fuel cells. These are small residential micro CHP units for a family, one family houses, for apartment houses, and different power ranges. Industrial as a prime power for data centers, for example. Microsoft currently has more than 100 data centers. Each data center actually is about 800,000 racks. Each rack is about 10 kilowatt. So it's a huge power demand inside the data center. And then currently they are grid dependent, so they have to build very expensive backup systems in data centers in order to be, reliable. But it costs a lot, so much easier is to put, for example, the small fuel cell system on top of each rack inside the data center. And then therefore you have also not only data redundancy, but also power redundancy inside the data center, even if one fuel cell system fails, for example. So, and of course transportation, because the efficiency of a transportation system currently is extremely low, even lower than the power production. So this is something we have to do, and then there are several possibilities using PEM fuel cells as a main power sources for electric vehicles, or also SOFC, high temperature fuel cells, as a range extenders or auxiliary power units for trucks or passenger vehicles. And of course storage, because hydrogen, as discussed earlier, is the most efficient way of store energy, but I come to that later. But not only efficiency, it's also about air quality. So, yeah, it was also discussed earlier that fuel cell power plants are virtually emission-free. So even if you use natural gas as a fuel, so you actually emit about 2 to 3 times less CO2, and other like NOx or particle emission is practically zero, which is a very great contribution to our environment. And talking about clean air, we have to address also renewables as wind and solar. So what we have seen in wind and solar, that this is growing and growing very fast. So there are some expectations how fast it will grow, and it's always, some doubts, is it really growing so fast than we are thinking about? But if you look back in the history, actually both solar and wind has grown much faster than has predicted, and it has been always so. For example, here we can see that it's predicted about 440 gigawatt installed cumulative in the whole world, 2020. But actually in China, already today is about close to 120 gigawatts installed. This year already close to 40, only this year. So it grows extremely fast in China, for example, and then China already now is fulfilled their 5-year plans target for 2020. It's already done by today. So it's going very, very, very fast. Same happens with wind. And imagine by this graph, you can see that about 1.2 terawatts of intermittent capacity will be installed by 2030. But already now, grid in some areas does not accept wind. So what should we do? We should find the best way for storage. And this is pretty good illustration about how we can store. We have different storage technologies which are mature, we know them, but they all have some kind of limitations. Supercaps are excellent for instant. Batteries, we know all batteries, but we can't store in batteries for a long term. And of course we can go quite big with batteries, but again, it's not very efficient. Compressed air, pumped hydro is also very well, it's mechanical, you can use it for a very big capacities, but not very flexible again. So, and here you clearly can see that if you really want to store for a long term with high efficiency, you have to store it into hydrogen. So this is quite clear, so you can do it for several months. And then where to store, small amount you can store in gas pipes, larger amounts even in underground caverns, in compressed ways, or a lot of ways how to store hydrogen in very, very cheap way. And if we talk about the hydrogen production, then electrolyzer is one of the ways to produce hydrogen from excess power. So, but there are also different fuel cell systems which can act as electrolyzers. So fuel cells can not only produce electricity, but they also can produce hydrogen from electricity. So low temperature fuel cells like PEM water electrolyzers or alkali electrolyzers, which are alkali especially quite established technology already, can produce 1 cubic meter of hydrogen using 4 to 6 kilowatt hours. But when you go higher with the temperature, in case of solid oxide electrolysis, you can bring the energy uses down to 3 kilowatt hours per cubic meter. So this is again efficiency. And also graphically here about how really to use this hydrogen. So it's not only to store hydrogen, but in some cases you can use it immediately for transportation, for example, or to produce synthetic fuels. So it's actually, or in chemical industry. So it's actually endless way of using hydrogen, not only storing and producing electricity back when needed. So to conclude this part of presentation, I will come back to this very wise scientists I referred this morning and show again these nice quotations from the book and what Oswald has told about the fuel cells and how the fuel cells really are the most efficient way of producing electricity or converting energy. Using this possibility here, I also would like to present briefly what we are doing here in Estonia in terms of fuel cells. So at Elcogen, we have worked with fuel cells already for 16 years. Last 5 years we are commercial, so we sell our products currently to about 60 customers worldwide. We see clear demand and growth of this demand from our customer side, so we are now planning to increase our cell manufacturing and stack manufacturing capacity in next 4 to 5 years. And really we have put a lot of manpower into this research, so basically we can count about 350 man-years of research what we have done. And currently this is again our customer feedback, so the best technology available currently in the world. And this is also reflecting here, so basically about 65% of our products currently is going to Japanese market. So from Europe, really we can serve also other areas, and with this great knowledge that we have here in Europe, and also created by using this very good funding of instruments from EU, which has been discussed earlier in presentations. And we really hope that this funding will continue, because now we are in a very nice situation that we are just in next 3 to 4 years are going to be commercialized and going to really big markets. So for that, a lot of financing is needed, especially for the production ramp up and market entries. So what we are doing here, we are not producing fuel cell systems. So our product is a fuel processor or single unit cells where actual power conversion process is taking place. And we are currently only company in the world who really can produce ceramic cells operating at 650 degrees C. And why this 650 is important, we can use industrial grade, low cost materials in stack and system level. And this is one thing which helps to bring the system cost down at the required level, and also enables longer lifetime of a system. And this is actually this holy triangle we are addressing: efficiency, cost, and lifetime. So, and we believe that by lowering the operating temperature of solid oxide fuel cell technology, which is the most efficient energy conversion technology, we can really achieve all these, especially cost targets, which we expect to be as low as 500 euros per kilowatt in mass manufacturing. Lifetime of 40,000 hours we have already confirmed by our tests, about 9,000 hours, and efficiency also in stack level is confirmed during 2 EU projects which we have done, and it actually the same value is measured in 2 different research institutions. So this is a stack level conversion efficiency from the natural gas lower heating value, and this is electrical efficiency, not overall efficiency. So this is, we think, currently, as we know, it's a world record in energy conversion efficiency. And also it was discussed earlier that there are several applications, and our customers also currently are in different applications. We serve residential and micro CHP as well as industrial CHP, and also a few customers in automotive industry and also in power storage. So that's shortly my contribution to this seminar, and now we have a chance to refresh ourselves, walk around network. I think we have some food here, and once we're done with food, so we can continue our next sessions. Thank you.